So now we want to practice two things. We already saw experience of doing a one-tailed hypothesis test. Now we're going to not only test a two-tailed hypothesis, but also practice our p-values. Two birds. So let's say we work at the Ringling Brothers Circus and we want to evaluate the state of our jugglers because that comes up and they hire statisticians for some reason. So you're testing if the average juggling time differs from the historical average of 120 seconds. Okay, now I'm going to explain why this is going to be a two-tailed test. First, so we have the average of the population, and we don't know how the juggling has changed. Maybe people got significantly better over the years, and so we want to look for any extreme values in the higher end. But also, maybe people have gotten a lot worse at juggling. There's clown colleges are struggling for funding. It's harder to find a position. Maybe just the overall quality has dropped, and so maybe we also want to consider the lower end of things. Okay, so we take our uncertainty, usually 5%, but it could be 10% or 1%. But we want to take our uncertainty and distribute it to both sides. So if our uncertainty was, let's say, 5%, 0.05, we want to distribute that as in half of 5% or 2.5% on this side and then 2.5% on this side to add up to our total uncertainty of 5%. And it's harder to prove something in here because, as you saw in my last explanation, when we find a critical value, if we're looking for just greater or less than, we can spend all of our uncertainty to one area, and so it's more likely that our t-score or z-score will lie inside of the rejection region. So it's a little bit harder to prove something when we distribute the uncertainty on both ends, but we can also account for if it's on both ends. Okay, so step one is always the same. We want to form our hypotheses. So our null hypothesis, the hypothesis that means that we are not going to consider anything significant, we're not going to make any conclusions, or default is that there has been no change since the historic average. Okay, so we're saying that the average of our clowns, or I guess everyone can juggle. Why am I leaving us? But our average is 120 seconds of juggling, solid 2 minutes. Okay, but now we want to see enough evidence to move us in one direction or other. We want to see significant enough changes to change our mind that there has been a change in juggling, whether that's improved or declining. So we're going to say that the average time for alternative hypothesis is not equal to 120 seconds. Okay, it could be higher, could be lower. We just want to prove that it's far enough away from 120 seconds to be statistically significant. Okay, and that's why this is two two-tailed tests. So, step 2. So these steps are the same, but we're going to obtain our data. And I'm going to save us some thinking power here. We already know how to find the mean of data. We know how to see if we're given the population standard deviation or we have to derive it. So I'm going to combine steps 2 and 3 for brevity because we all have better things to do than practice things we've been doing since we're week 2. And so I'm going to find the sample average. And this is all going to come into several facts. First, we're going to assume we know the population standard deviation just for the sake of ease, because sitting through a calculation of a estimate of a population, the estimate of the population standard deviation is long. We've done it 100 times, but we're just going to say the standard deviation of the population is known to be 20 seconds. This is like the average distance from the mean. This is how consistent we are. Most of our data is within 20 seconds of the average. Next, we're just going to say that from our data. our recent clowns, jugglers, everything in between, I guess. But oops, always got to use the right symbols. X bar, our sample average, is equal to 100 and what will we say? How about 125 seconds? Okay, so we sampled a bunch of people. We're going to say we sampled 40 people. We sampled 40 people who are current jugglers, and their average is 125 seconds, which is higher than 120 seconds. But with this many people, this concentration and consistency of data, and this average, we're going to see if this is convincing enough in a two-tailed hypothesis test to convince us that the jugglers have changed. Okay, luckily we can go to step 4 currently. And that is finding the test statistic. See, all the steps are the same so far. Okay, we're doing a z-score because we have a population standard deviation. Otherwise, you already know we'd find the t-score using the sampled data and the sample standard deviation. The z-score in this case is x bar minus mu, the difference between our sample mean and the historic average, over population standard deviation divided by the square root of how many people we sampled. Okay, you've seen this calculation before. We just plug and chug. Total difference of 5 over given standard deviation of 20 divided by square root of 40. And that's equal to 5 over, if you plug into your calculator, 3.1623. So we can see our z-score is, we're always going to be approximate squiggles because we rounded to 1.58. Lovely. So now remember this value represents how significant our data is, how far we are on this from 0 on the normal standardized curve. This represents how many people we sampled, how consistent our data is, and our deviation. Are we different enough? And it packed it all in this score, and we're going to see if this is an important enough score. Now we know how to, we could just plug this into a critical region. And so our decisions from moving forward with everything we know is that we have two choices. First choice is that what we've been doing, is this more extreme than extreme enough? This is what we were doing with hypothesis testing, where we found the critical region, where in a two-tailed case, we'd say, okay, these are regions to be concerned about. We'll say that this is our 2.5% distributed to each end. So anything that lies either here in this lower end or here in this higher end are critical enough. They're important enough. They're different enough to be considered statistically significant. Okay, this is what we've already just done in our examples. Now we can approach it with the p-value approach, which asks, is this value unlikely? I want to get the wording right on this. Oh, where'd my pen tools go? They're there. Is this value unlikely enough to convince us? Or p-value says that we're going to assume that the null hypothesis is true. So how, if that was true, how weird is it that we saw a data point so extremely in one direction by like just a fluke of sampling, like chance? And that's what we can calculate. We're going to calculate how likely it is to see that value or one more extreme than it. And then we can get a good idea of if it is something that is going to convince us out of our null hypothesis. So anyway, we finished our step 4, finding the test statistic, which is 1.58. Now, because we're doing, usually our step 5 is to determine the rejection region. But that was when we were doing it with option 1. Okay? And we have already seen videos on how to do that. Now we're going to slightly change this. Now, this step 5 is to determine the p-value. And that'll tell us if we can safely reject the null hypothesis by assuming it's true, then seeing if our data is just so overwhelmingly weird to convince us out of it. Okay, we can do this 2 ways. We're using the z-score, but we can either use the table or our calculators. On quizzes and exams, I'll always provide the table if your calculator is having issues, but calculator is usually the more accurate way to go in the real world. Okay, so using the table, let's get our table back out of here. Okay, we got our table right here. And it looks like this table is to look at whatever is at a certain value and more extreme. So I was looking at the t table by mistake. So we're looking at the z tables here and here. We're going to use an argument from symmetry in just a second, but you can see that from left to right, this is the amount of area it's covered. Okay, so when looking at our value of 1.58. Okay, so 1.58. 1.58 would obviously be in this upper region. Okay, and because this is symmetrical, it's going to let us know that we can look at the negative value and find this area. And this is how I'm going to explain this is going to work. It's going to look a little bit odd. Let me just grab this value. Z equals 1.58. Z equals 1.58. Okay. So when we're looking at this table, it obviously fills up from left to right. Okay. And because we have two, wow, this is not a straight line. I need to get that checked. There we go. Clean this up because we care about our diagrams in math. Take more art classes, you guys. So when our table is saying, oh, this is the amount of area from left to right, and because we have a two-tailed t-test, we need to worry about what's on both sides. So to find out the likelihood that we found this extreme value or something more extreme in either direction is that we're going to say, okay, this is 1.58, and because of the symmetry of the standardized normal curve, which has a mean of 0, this left tail will be at negative 1.58. So because we want to find out, this is the extreme of our data. We want to find out what the likelihood of finding that or something more extreme. And in two tails, we want to account for both sides. So what we're going to do is we're going to take this, find out the amount of area covered with negative 1.58, and then because of symmetry, we can double it to find out this is the likelihood of finding data by chance in either direction. Okay, so let's see. So there we go. So negative 1.5. Oh, might as well find the 8 up here. Hold on. Okay, so it's this column. Let me move down. Negative 1.58 is right here. Okay, 0.571. 0.571. Okay, so that's the area of this side. And then we multiply it by 2 to get both sides for a two-tailed t-test. So 2 times this value is, let's consult our handy-dandy calculator. Here. 2 times 0.0571 is equal to 0.1142. 0.1142. And that is our p-value. Okay, so there's an 11.42% chance that we just had a fluke of data recording and we saw that. Now remember, in the notes, we want this to be, if we want to be 95% confident, we want this to be less than 0.5. So at this p-value, we fail to reject the null hypothesis in favor of the alternative hypothesis. And always remember, that's not proving the null hypothesis. We never prove our starting point, ever. That's so important. We just failed to see convincing enough evidence to confirm the alternative hypothesis. Okay, and that's how to do this with a table. Okay, we can also do it on the calculator. So the same process without a table. We're going to do the same thing, where we say 2 times, because we're going to find the total area up here of one side. And we've seen the normal CDF function we've used before. We're happy with it, comfortable with it. And we want to give it the values. We were just going to find the right side of the right tail and then multiply by 2. So we start at z-score of 1.58, comma. We want to go to infinity because we want to consider everything on the right side. So we're just going to do 10 to the power of 99. Seems like a big enough number, comma. And then the average, it's a normal standardized curve, so it's 0. And then a standard deviation of 1, also characteristic of this curve that we're using. So 0 and 1 will always be the case for this particular calculation. And that's 11.41. So when we don't use the table and we have more accuracy, we can say that the calculator gives us the p-value of 0.1141, slightly more accurate, but still confident enough, or not confident enough to reject the null hypothesis in favor of the alternative hypothesis. Okay, so that is exactly how we'd approach this with a z-score, and we can also know how to do this with a t-score as well. Just to show you how we know how to use the t-table, but let's also finally learn how to use the calculators for this, because it's always so helpful to use the calculators. We're going to be doing the same thing. Let's say hypothetically we did this whole process and we find a t-score of 1.92. Hypothetically, that's just being pulled from nothing. Okay, if we saw this and we had all this data, then we can do the same thing we were doing here 2 times. Instead of the normal CDF function, we're going to use t-CDF because we're using the student t-distribution. We plug in our lower bound, our upper bound, and here all we plug in is the degrees of freedom with 40 data points. Degrees of freedom are n minus 1 equals n minus 1 equals 40 minus 1 in this case, which gives us 39 degrees of freedom. Okay. Now let's literally plug that in 2 times, because we're just doing the upper curve, second distribution tpdf, type in our lower bound, which is 1.92, comma, our upper bound 10 to the power of 99, comma, and degrees of freedom, which is 39. I said I made up this t-score, doesn't represent anything, but got mad at us. 92. Oh, hold on, let's see why it got mad at us. Let's try that again. Hold on. 2. Sometimes these calculators can be tricky to deal with. Oh, did I hit PDF before? Maybe, I think it's because I hit PDF before instead of CDF. Make sure I'll listen on what not to do. 1.92, comma, 10 to the power of 99, comma, and then 39 degrees of freedom. Let's see if that fixed it for us. Oh, yeah, there we go. So in this case, we have a p-value of 0.06, which, if we want to be 95% confident, is above 0.05, so that we would fail to reject the null hypothesis. But if our confidence was, let's say, 90%, then this would be fine because we would want our confidence to be below 0.10 for the 10%. And so we can be 95% confident. We can't be 95% confident, but we can be 90% confident. And here's also an ethical tip I really want to impart. This might pass for the 90% confidence, but it does not pass for the 95% confidence. Okay? And I just explained why, but it's vital for ethics and quality of work that we decide how confident we want to be before we finish anything. Like, we want, at the very beginning when we're proposing the hypotheses, we want to decide we're 95% confidence in this, and then we'll see at the end. We can't just choose a confidence after the entire analysis, because that's just cherry picking, and that is wholly unethical. Okay? I guess nobody can technically stop you, but it's very poor practice. It'll lead you to a lot of very poor results, because you'll end up relaxing your conditions, and then over time you'll be accepting a lot of things that are just a statistical fluke. Okay, so yeah, we just explore how to do two-tails and p-values. So we just got a little bit more practice under our belt, and that's cool.